Welcome, Daniel, to Func Prog Sweden.
Hey everyone, thank you so much for having me here. And I'm gonna try to pitch Scala to all of you in this talk about Scala and functional programming and how Scala can be a purely fun language to work with. My job here is to demonstrate the nice features of Scala that make it such an expressive language, and hopefully at least one person in this room or maybe watching this presentation might take away this lesson that, oh, Scala might be such an interesting thing to at least try in a pet project before we spin it up at our day job or something like that. So welcome everyone to a sweet guide to Scala for beginners. I've been told that not everyone in this functional programming conference is a Scala developer. So hopefully we'll have a chance to talk about Scala for seasoned developers, but for people that haven't seen Scala before. My name is Daniel, and I am a software engineer and teacher. I've been teaching Scala for a while, and I've had the privilege of teaching more than 70,000 people all over the world at this point, and have the opportunity to train some high-performing teams at some of the the highest profile companies in the world, like Adobe and Apple and Microsoft and that sort of stuff. So I've been teaching Scala out of passion. I love this language and I love the ecosystem and the tools. And I founded this website called Rock the JVM, which is a learning platform for pretty much everything in the Scala ecosystem, not just the Scala language, but functional programming, tools like CATS and CATS Effect, Apache Spark, Apache Flink, Akka, and so much more. So my job in this talk is to give you a glimpse of what Scala can do. And the way that I like to present and teach things like Scala is not so much with slides, although they do help with some diagrams that are impossible to demonstrate with just hand waving or in code. But my style is mostly live coding. So I'm going to attempt writing code for most of this presentation to just show you how Scala can be such an expressive language to work with. So without further ado, I have here a pretty empty project in IntelliJ IDEA. And I have here a simple Scala application with a main function. Those of you Scala developers or even Java developers might recognize this sort of structure. So this is pretty much a class with a static main function that takes an array of strings and returns unit, which is the Scala way of defining void functions. Scala is, most of you, I'm pretty sure you know, there's a statically typed language, unlike Clojure. So the compiler does a lot of work for you and infers types and so on and so forth. So I'm going to demonstrate some of those functionalities as we go along. And this main function will be used just for us to test some stuff, just so we can see how things work when we actually execute them. So given no background in Scala, I'm going to try to explain at quite a fast pace some of the nice stuff about Scala and how Scala can help you think differently and approach code in a different way. And hopefully by the end of this talk, you'll get a glimpse of how you can extend functionalities of existing types, how you can write natural language like code, and just have the compiler do a lot of things for you and compile only for those pieces of code that you want to compile, therefore making the compiler do a lot of work for you to validate the correctness of your code. So this is the general gist or the general objective of the talk. Now, I'm going to start with zero knowledge of Scala prior. So we know about Scala that is object-oriented and functional in the sense that it blends the advantages of Java. So Scala was built initially for the JVM, which is object-oriented programming, plus the higher level functional programming principles on top of those. So we are going to also see how functional programming can be built on top of the JVM, which was originally built for an object-oriented language. Java is one of the canonical O languages. So in Scala, we tend to think of values and expressions. Values are essentially these constants that you cannot change. Of course, we have variables that can be changed with time, but the idiomatic Scala way would be to define values which are essentially unchangeable constants. So let's call this value meaning of life. And this meaning of life is obviously 42, as we all know. Now, the compiler can infer the fact that the meaning of life variable is of type integer. So I can write this type, but I don't have to write it because the compiler infers that for me. So we know that meaning of life is an int without us writing the definition for it. This makes a very powerful compiler because this speeds up our development process without taking the types out of our head and leaving them to the compiler to figure them out. Now, we tend to think of these as constants because we cannot change them. And we also tend to think in functional programming with values and expressions. So in my beginner Scala courses and trainings, I teach people that unlike the imperative style that they're used to write, most of them, in Java or in Python or in C++ or that sort of thing, we tend to think of code as instructions, like things that are executed step by step and making the computer repeat some stuff and do things conditionally and so on and so forth. But we tend to think in algorithmically, step by step. Rather, in Scala and in functional programming, we think in terms of constants or values and expressions that build upon these values to produce new ones. And our programs, our functional programs, are essentially one giant expression computing value. So expressions are everything in Scala, or rather backwards. Everything in Scala is an expression. Even if statements, even for structures are also expressions. Let me give an example. So if I define a val, let's call this if expression. This is, let's say, if 2 bigger than 3, then I'm going to return the string bigger, else smaller. So unlike other languages where we say if 2 bigger than 3, then do something, otherwise do something else, this whole bit is one expression, meaning that this can be evaluated or reduced to a value. This is the fundamental difference between an expression and an instruction. So in Scala, forcing constants and expressions naturally force us to think differently. So Scala and functional programming incentivizes us to think differently. And one easy way of thinking differently, with respect to simple code at least, would be to completely make do without loops. Because there's nothing to change, then there's nothing to loop for. So we say that loops can be simulated, or rather redone, as recursion. And functional programming experts will be masters of this. So recursion would look something along these lines. In natural, let's say, more common languages like Java, let's say if you wanted to sum the first n numbers, we would define a function, let's call this sum n, where we have an int n, and this returns an integer, and then we would say int sum equals 0, and then we would say for int I equals 0, then I less than or equal to n, something like that, and then we say sum plus equals I, and then we would say return sum. So this is the algorithmic step-by-step instruction-based thinking. But in Scala, we are forced to think differently because there are no variables. There are variables, but the idiomatic way of writing Scala code would be to ignore variables because, as functional programmers already know, variables make for some hard to read code, hard to understand, how to debug, how to reason about, and so on and so forth. So the natural expression-based way would make code much more understandable. I'm going to simply demonstrate how that works in Scala. So I'm going to define a sum n function that takes an n as an integer and returns an integer, but of course, because the compiler infers types already, I don't have to write that myself. So I can say if n is bigger than or less than or equal to 0, let me define the base case. I'm going to return 0. Otherwise, I'm going to say n plus sum n with n minus 1. So notice that at this point, we've defined a recursive function, which does pretty much the same thing. Now, for recursive functions, I do have to specify the types because the compiler will rely on the expression that the function will implement to infer the type, but because the expression already contains the function definition, the compiler is stuck in a loop. So I have to help it by specifying the type beforehand. That's just for recursive functions. So notice that in just one expression, I can compute pretty much the same thing as I did in an imperative style in Java. So Scala forces us to think differently. This is pretty much the first takeaway. And I think I wrote this in a different comment here. So think differently. Now, thinking differently involves a variety of aspects in functional programming and in Scala. And in this talk, I'm going to attempt to demonstrate bunch of those, hopefully limited by time. So this involves a different mindset. Scala also has fully object-oriented programming in terms of classes, interfaces, extensions, inheritance, polymorphism, generics, and much more. So I'm going to simply give an example. I'm going to define a class person, and when you define a class in Scala, you also define its primary constructor right off at the bat. So here at line 28, this class person also has its primary constructor, let's say a name as a string, and a favorite language, or favorite programming language, of course, as a string, because every person must have a favorite programming language, of course. And you can obviously define methods and fields and so on and so forth, just like you can in other object-oriented languages. For example, I can define a method called likes that takes a conference as a string. And this one will return a string, but obviously the compiler can infer that, so I can simply implement that right off the bat. So I'm going to say s-quote, and s-quote is pretty much an interpolator. If you've done any TypeScript or JavaScript before, this allows injecting expressions or other variables inside the string so that you don't do the weird a plus space plus b plus space that we used to do in Java. So I can say name likes conference. So right out the bat, so we have the likes method returning a string. So if I hover over this, we know that the method returns a string. This is inferred by the compiler, and the IDE is smart enough to figure that out. Now, one nice thing about object-oriented programming in Scala is that Scala makes these sort of methods that take one arguments very nice to invoke. For example, let me define a val called Daniel as a new person with the name Daniel and the favorite language. It's obviously Scala. Now, I can call the likes method on this person. So I can say Daniel Func Prog, Sweden, of course. I can say Daniel.likes functional programming Sweden. So Func Prog Sweden. And this is the natural dot notation that we're used to from the C family of languages like Java or JavaScript or C or C# and that sort of stuff. But with methods that take only one argument, you can also call it in a very natural language style way. So I can say Daniel Func Prog version 2 as Daniel space likes space Func Prog Sweden. And this is the exact same thing. So notice the natural language approach to calling methods. This only works with methods of one argument, of course, because if you have multiple arguments, the compiler can't tell whether you're chaining arguments or you're calling some other method, because of course you can chain them. So you can say Daniel likes Func Prog Sweden. What natural English almost code that is. Now, you can also have in Scala, we have very permissive method naming. For example, you can define non-alphanumeric methods. So I can say def may invoke some sort of symbol like triple exclamation marks, conference as string, and let's say that I'm simply calling likes on that conference so that I don't have to duplicate the method. This triple exclamation mark is a valid method name in Scala. And combined with this infix style, this is what this method notation is called, we can define something like this, like Daniel Func Prog version 3 as Daniel and then a space, and then I can call this new method that I like, which is triple bang, Func Prog Sweden. And this is for mathematical like notation for various abstract libraries like cats or cats effect. If you've heard of those, they use these sort of methods very, very often. So Scala and functional programming go hand in hand in this case, also because of this simple approach to method naming, because all our expressions can also be thought of as mathematical expressions. This is very, very nice in Scala. And this is not some rocket science that the compiler does behind the scenes. It just converts this infix style into the natural dot notation that the JVM understands. All right. There's also another method, another special method in Scala called apply, which is very, very powerful for functional programming principles on top of the JVM, as will become apparent shortly. So if I define a method called apply, so I'm going to say apply with, let's say, language as a string, and this return Boolean. And I'm going to simply return true if this language is equal to the favored language. So I'm going to say language is equal to favored language. Now in Scala, the double equals is the dot equals in Java. So this thing is automatically the equal sign in Java. And because we're using strings here, the equals method will obviously return the right thing for the right strings, even though the strings instances themselves might be different. So apply is special. So I can say Daniel likes Scala as Daniel.apply with Scala. And this, of course, is true, but the value of this method is not that important. The form is what's important. The apply method allows an instance of this class to be invoked like a function. So I can say Daniel likes Scala version 2 as Daniel invoked on the string Scala directly. Notice how powerful this little trick is. Once we've defined an apply method in a class, we can invoke that instance on a bunch of arguments. Of course, the apply method can be overloaded. It can have multiple arguments and so on and so forth. And we can simply invoke that instance on those arguments as if it were a function. Now, this is a very powerful trick because this allows functional programming on the JVM. Now, before we deal with functional programming on the JVM, I just wanted to mention the fact that Scala also has the traditional object-oriented features. So we have abstract classes, we have inheritance, we have interfaces. In Scala, they're called traits. We have generics. We have polymorphism. And the natural things that we know from canonical object-oriented things like Java. Now, switching to functional programming on top of the JVM, we know from experience that functional program, and also from the definition of functional programming, of course, that functional programming's objective is to be able to work with functions as quote-unquote first-class citizens. What does that mean? First-class citizens means that we want to work with functions like with any other kinds of values in our programs. So we want to work with functions like we do on numbers, on instances of classes, and so on and so forth. So we have to be able to compose them. We have to be able to pass them as arguments. We have to be able to return them as results. We simply need to be able to associate them to variables. Now, how is this principle going to work on top of the JVM? Well, the JVM was built for Java, of course, and Java doesn't have this notion of first-class functions. Obviously, it does have Lambda functions, but that's not necessarily a first-class thing on top of the JVM because you can't associate or you can't work with these sort of lambdas like you would in a purely functional language like Scala. But the way that Scala implements the functional programming ideal on top of the JVM is to define these sort of special traits called function 0, function 1, function 2, and function 3, and so on and so forth, and grant them this apply method, which gives them the ability to be invoked like functions, of course. Let me give an example. So I can define, let's call this multiplier, as a new function, let's say function 2 that takes 2 arguments. Notice that we have function 1, 2, 3, 4, 5, 6, 7, and so on and so forth. So we have special traits that are built into the Scala standard library. Function 2 takes a bunch of type arguments. So these square brackets are the equivalent of angular brackets in Java, the generics in Java. So I can say int that so these are the quote unquote arguments of the function. And the third type argument is the return type. So new function 2 with int, and function 2, because it's a trait, I can instantiate it on the spot with anonymous classes. So I can override the apply method. So function 2 has this fundamental method called apply. Let's call the arguments x and y, then actually called v1 and v2 because they were generated. So I can say x times y, for instance. Now I'm going to collapse this code because the implementation is not that important. What matters is that this multiplier is an instance of a type that the JVM understands. Now, of course, I can say val, let's call this 12, as multiplier dot apply, because that's the fundamental method of the function trait. And I can say 3 and 4, and obviously I'm going to return the number 12. But because the apply method is special, as I've just described, we have, let's say, 12 version 2 as multiplier invoked on 3 and 4, which makes this multiplier thing pretty much be a function. So the functional programming ideal was based on a very simple trick. Just create function traits in the standard library and grant them this apply method, which gives them the ability to be invoked like functions. And because this is just an instance of a type, much like any other type on the JVM, you can pass it around. You can pass it as arguments, you can return them as results, you can combine them with any sort of methods, you can write any sort of thing with these types. So the functional programming principle of having functions as quote-unquote first-class citizens is implemented on the JVM with these function types with apply methods. Now, if this isn't quite magical and this is a quite simple trick that the compiler can work, then I'm going to back off. I don't know what else can be magical on top of this. So these function types are traits, also known as interfaces in Java. All right. Now, we can also define, or rather, Scala defines type sugars for function 1, function 2, function 3, and so on and so forth, because typing this sort of stuff is quite tedious. So I can say val multiplier version 2, and this is of type int, arrow, int, which is syntactic sugar for the same function 2 type. So if I remove int, arrow, int with function 2 type, these are exactly equivalent. So I'm going to keep it like this. And I can say xy, arrow, x plus y. So the kind of syntax that you're familiar with from other functional programming languages, or even from the object-oriented languages that brought in functional programming elements. So you know this kind of syntax, xy, arrow, x plus y. But Scala goes a little bit further than that. And a bit to the extreme, if you can read such compact code, I can say multiplier version 3, again as the type int, arrow, int, and I can say underscore plus underscore, which is pretty much the shortest lambda that you can possibly write. Each underscore means a different argument. So if you don't really need to use these arguments more than once in the implementation, all you care about is the expression itself. And this is the rawest form of expression that you can possibly have. It's like just writing plus in Clojure or in Haskell or that sort of stuff. All right. But of course, the writing something like plus doesn't quite work. In Scala, you have to use this sort of syntax, which is pretty damn close. So notice that Scala has all these kinds of sugars and tricks that make it a very expressive language and a natural functional programming language on top of the JVM with these sort of tricks that I've just described. All right. Cool. So these are essential functional programming elements on top of the JVM. Obviously, in a course or in a training like this, I would spend pretty much half a day just talking about this and what the kind of higher order functions that Scala supports and so on and so forth. But I think you got the idea. The goal of this presentation is just for you to get some principles and some ideas of how Scala works. Obviously, we have the map, flatMap, filter, and so on and so forth that you see in other functional programming languages. So for example, I can say a transformed list as list applied to 1, 2, 3. So when you say list invoked on 1, 2, 3, obviously this is the apply method, because you now know that the apply allows this thing to be invoked like a function. So list 1, 2, 3. And then I can say map. And obviously then I can do a transformer on every element. So I can say underscore plus 1, let's say, and this will be the list 2, 3, 4 as we can probably expect. So we have list123.map, and this expression is obviously a lambda that you can write in this very shorthand form, or you can say x arrow x plus 1 if you'd like to be more explicitly, or if you want to be really verbose, although I've never seen this happen in practice, with a new function 1 taking an int and returning an int where the apply method is whatever. All right. So everybody writes something like this because it's very easy to understand. And when you look at a one-liner like this, after 5 minutes of learning Scala, you know what it means, and you can read it very easily, which means that Scala is a pretty readable piece of code. So when you write 20, 30 lines of Scala, they can do a lot because the Scala code is very compact, but you can read them very easily. It's quite natural to see that this is a transformed list. I can say, let's call this a bigger list as a list 1, 2, 3, and then I can do flatMap. So flatMap takes a function from an element to a mini list. Let's say list and x plus 1. And flatMap, I'm not sure how big of a functional programming background this audience has, but assuming that you're watching this video and you have no idea how flatMap works, flatMap takes every single element of this list and runs this little function, which basically turns each element into one mini list, and all the mini lists are combined into one. So in this case, we have a list composed of 1, 2, because this is the mini list obtained from element 1, then the elements 2, 3, the mini list from element 2, and then 3, 4, the mini list from the third element. And these are compacted into one. Now, map and flatMap in Scala have the capacity of being combined into chains because that's a useful programming pattern, and this happens all the time when you process collections, when you process streams, when you process any other data types that have map and flatMap, for example, effects or monads. I know we have a monad tutorial or a not monad tutorial at the end of this meetup, so I'm not going to go there too far. But map and flatMap will allow us to write a very special structure in Scala called a for comprehension. So let's call this checkerboard. And in this checkerboard, I'm going to combine two lists, let's say a list of characters and a list of numbers, and I'm going to obtain all the combinations between them. Now, in Java or in an imperative language, we would have to do a double for loop and combine every element with every other element and so on and so forth. But in Scala, we would have to write something like this. Let's say list A, B, and C, and then I'd say flatMap, because for every little element, I'm going to return a mini list. So I'm going to call this character. And then I'm going to say list 1, 2, 3, 1, 2, and 3. And then I'm going to call map on every number. And then I'm going to return an S-interpolated string, let's say character dash number. So for every little character, I'm going to return all the combinations between 1, 2, 3 and that character. Of course, once you've exhausted the characters, we've obtained all the combinations between all the characters and all the numbers. And in main, if I do a print line, so if I do a print line, and I'm going to use this checkerboard thing. If I run this application, we're going to see all the combinations between the characters A, B, C, and the list 1, 2, 3. So we have A1, A2, A3, B1, B2, B3, C1, C2, C3. But the map and flatMap chains in practice can get quite long. So in Scala, we have this magical expression called a for comprehension. So we have this checkerboard. I'm going to use checkerboard version 2 as a for comprehension. So this is not a loop. So I'm going to write this in all caps for everyone to understand. This is not a loop. This is an expression. And I'm going to tell you what kind of expression it is. So I'm going to say car in list with A, then B, and then C. And then I'm going to say number in list 1, 2, 3. I'm going to say yield. And I'm going to use this sort of expression car dash num. So I'm going to paste it here. And this checkerboard version 2 is exactly the same as above. Now, not similar, it's identical, because every for comprehension in Scala is reduced to a flatMap and map chain. So whenever you see a for comprehension in this way, which is far more readable for us as usually imperative programmers before we turn functional programmers, this for comprehension is actually turned by the compiler into map and flatMap chains. So if I do print checkerboard version 2, then this will give us back the exact same result. All right, so we have the list A1, A2, A3, B1, B2, B3, and C1, C2, C3. But the for comprehension is far more scalable in terms of code, because you can simply add another generator here, another line, and then you combine 3 lists and then 4 lists and so on and so forth, rather than writing flatMap all the way. All right. So for comprehensions are incredibly powerful in Scala, and this is pretty much a syntax sugar for map and flatMap chains. Now, I hope I've convinced you that at least for essential code, Scala is a pretty powerful and expressive language, which turns very compact code into something that's very powerful and does a lot of things behind the scenes, without sacrificing readability, of course. One magical aspect of Scala, there are multiple magical aspects of Scala, but one truly magical aspect of Scala is called contextual abstractions. Contextual abstractions are a set of features in the Scala compiler that will only allow you to compile your code under certain conditions, and the conditions are yours to control. For example, I'm going to write something along the lines of a sorted list. Let's call this a sorted list as list, let's say 4231, and then I'm going to call sorted. Sorted only compiles for things that already have an implicit ordering. That means that there has to be somewhere defined in other pieces of code that you can import a value that can compare 4, 2, 3, and 1, the integers. The Java analogous to that will be a comparator object. Comparator, I think. The way that this works is that we have 4, 2, 3, 1, and that comparator is passed automatically at the sorted method. So if I print this sorted list, we will see the natural order of integers being shown in this list. So we'll see the list 1, 2, 3, 4. Now we can control that. We can say a given value. So the given value is kind of like an automatic thing that the compiler can inject into this sort of method. So let's call this automatic ordering, and this is of type ordering int. This is the kind of analogous to comparator in Scala. So I'm going to build one. So I'm going to say ordering from less than. I'm going to use underscore bigger than underscore, returning true between these two numbers, saying that one number should be before the other if it's bigger than them. So this is what this lambda is supposed to mean. Natural integer ordering looks like this, but the descending order looks like this. So I'm going to simply define an automatic ordering as a given, not as a value. Once I've defined that as a given, if I run the exact same code with absolutely no modification, we're going to see the list 4, 3, 2, 1. So this automatic ordering is being passed automatically. So automatic ordering, automatically, of course. We call that implicit. So we used to call these sort of values implicit because there is an implicit keyword in Scala 2. I'm writing Scala 3 as we're recording this video. So those of you watching from other sources like YouTube and seeing this in posterity, this code is written in Scala 3. So this is the latest incarnation of the Scala language, and the keyword for that is called given. And this given is passed automatically to the sorted method. If you carefully look at the sorted method signature, we have this keyword implicit ordering B. This means that the compiler fetches whatever given value there is in the scope and passes it automatically to this method. Obviously, you cannot create two givens for the same type because the compiler will not know which one to pick. All right, so this was the first contextual abstraction. One is called given. Now, the given values that are being passed automatically go in tandem with using clauses. The implicit keyword that you saw earlier was from Scala 2, which still works in Scala 3 for backwards compatibility reasons. But in Scala 3, the implicit keyword was so widely used for different purposes that the designers of the Scala language decided to split the meaning into multiple words. So the keyword now is using. So I'm going to define, let's call this method with automatic argument. I'm going to pass an argument as a string and the automatic value with a using clause. So let's call this amount as an int. This returns a string, and I'm going to simply repeat the string n times. So I'm going to say arg times amount. The times operator works like in Python. Now, I can call this method with automatic arguments. I'm going to say method with automatic argument with the string Scala, but the code will not compile. So here I have a compiler error because the compiler could not find a given value of type int that it can inject automatically. So you're the one to control which automatic values you can pass or whether you want to pass them at all. So this will pretty much help you prove the correctness of your code by controlling which using clauses you want to satisfy. So I can define, let's say, given, let's say, automatic int as having the type int, and let's assume I'm returning the string 3 so that we don't repeat the string Scala too many times. So now that I've implemented this given thing, then I can pass that automatically, or rather let the compiler pass that automatically for me. So if I print this in main, so if I do print line with method with automatic argument, then I'm going to see Scala being printed 3 times. I'm going to show you one other magical thing of Scala, and then I'm going to stop. So the second magical thing is extension methods. Extension methods have been around in Scala since 2012 or something like that, so well more than a decade now. And JVM languages like Java have yet to catch up with this concept. Extension methods will allow you to add new methods on types that do not have those methods. So for example, I can extend the int type, so I can say extension with n as an integer, and I can say def times with an s as a string, and I'm going to return a string and say s times n. So I'm going to do the same thing, repeating that string n times. Well, in this case, I'm going to say Scala times 3 as 3 dot times with the string Scala. So the times method now exists on this number. And this number means, the existence of this method means that I can now enhance my code with things that are more expressive. So I can say 3 times Scala. I can also call that infix, which makes it as close to natural language as you can possibly expect. So obviously, if I print this in main, I'm going to see a very similar result. So we have the string Scala repeated 3 times in the fabulous console. Now, these extension methods, as well as given and using clauses, so 1 plus 2 will yield some powerful abstractions. For example, type classes. Type classes are an extremely powerful concept in functional programming that will only allow you to invoke certain functionalities on certain types and not others, and make the compiler not compile your code if you're trying to invoke those functionalities for types for which you have not implemented type classes. And this leads to more expressive code and more modular code. Now, I would be absolutely happy to demonstrate type classes, but this will probably take another half an hour. So I'm going to stop here, and I'm going to simply invite you to join me at rockthejvm.com. This is my website. This is where I teach everything in the Scala ecosystem. Now, I'm happy to take any questions that you might have for me.
Thank you very much, Daniel. Super nice presentation. I really love that you made like a presentation coding and explaining the concepts and really showing like this is the steps, this is what you can do. Super nice presentation. I have one question that came up. Maybe you can or you can't answer it. Like, how does Scala compare to Elixir?
I have no idea.
No.
I have not touched Elixir, so I cannot really say. I do have something to say with respect to one particular set of libraries in the Scala ecosystem. It's called Akka, and Akka basically implements the Erlang model of actors, so that you can design your program in terms of these entities called actors that can exchange messages asynchronously. So in that sense, the Akka set of libraries will pretty much resemble the Erlang model. So you can design clusters of systems that can communicate asynchronously, regardless of whether those actors run on the same machine or on distributed systems, and so on and so forth. And there are a variety of tools based on them, such as streams and HTTP servers and cluster sharding and that sort of stuff.
Yeah, we have had a presentation, I think 1.5 or 2 years ago, exactly around Akka or Scala and Akka. As you say, very alike to Erlang type of thinking and doing things. Let me see. No, I don't have any more questions. As I said again, very nice presentation. I really liked it. It's really good intro, both to functional programming, but also to Scala. I'm not that into Scala myself, but thank you very much. Now I know more. So
that was my goal.
Yes, now I know more. You will find the links, and we'll post them to your channel at Rock the JVM. And we'll post everything below the video once we put it out, so people can find more introductions and presentations if they want to know more about Scala and your presentations and the stuff you've done.
Sure. And if anyone has any sort of questions about Scala, or if you're interested in taking any sort of training or course, just reach out to me at Daniel at Rock the JVM with any sort of questions related to Scala. I'm more than happy to help. And I'm active on Twitter at Rock the JVM, on LinkedIn, on YouTube, and everywhere. So you can check out my stuff at Rock the JVM.
For sure. People, take a chance. Ask Daniel. What would you show next? What would be the next concept to show or talk about in Scala?
Well, I could show you type classes, which is built on top of these magical features that I ended up with in my presentation. If you want, or until the next speaker comes up, I can start to do some demos.
Oh, do some demo. I would love some demo. If you have,
oh, really? Okay.
If you have some
right.
ready demos.
All right. Well, let's do this. Let me share my screen again, and let's get back to where I ended up with. So we were at contextual abstractions with given instances and using clauses and extension methods. All right. Good. Extending the live talk to type classes. Okay. Let's talk type classes. What are type classes? I mentioned earlier that type classes are a way to design your program in the sort of capability managed by the compiler. What do I mean by that? We would like the code to compile only for those types that have this sort of functionality, and we would like the code to not compile otherwise. So let's define some sort of example to motivate the need for type classes. Let's define a small library to transform data into, let's say, HTML. So we would like to transform data structures into HTML with some sort of serialization library. So the version 1 way, or the natural object-oriented way, would be to define a sort of trait, and we would define the sort of extensions or inheritance-based code. So I would say HTML writable, where we would have a method called toHTML that returns a string. And all our data types that we would like to convert to HTML extend this trait. So let me define a case class. So a case class is kind of like a data class, kind of like a record in Java, except Scala was doing that 15 years earlier. So hashtag brag. Let's call this user, which has a name as a string, an age as an int, and let's say we have an email as a string. This would be a user in our application. Let's say we're building a social network or things of that nature. And this, in the object-oriented way, would extends HTML writable. So we would have the toHTML method. So I'm going to say override. I'm going to override toHTML, and I'm going to use an S quote. I'm going to do a div, and I'm going to put that close. I'm going to do a name, and I'm going to say age, years old, and then I'm going to have a link to their email, and I'm going to say a href equals, and I'm going to use mail to, and I'm going to use email, things of that sort. Now I need to escape this stuff. So I'm going to say mail to email, and then I'm going to close my little tag here with a slash, not with a backslash. All right, I'm not a front-end developer, so excuse my poor HTML skills. You get the idea. So all our data types in the object-oriented approach would have to extend this sort of trait. Now, those data types that do not extend the trait do not get this functionality, which means that if I define a val called Bob as a user with, let's say, Bob and age 45, and this email bob@rockthejvm.com, we would say Bob to HTML as bob.toHTML, of course. So we only have this method for those data types that extend the major trait that we want to implement. But this comes as with major disadvantages. So I can define some drawbacks. For example, this is only available. Let me scroll down to see my comments. So this functionality is only available for the data types that we support. Adding a new data type will crash our entire thing because our data type is not an HTML writable. So if we are handling the sort of server-side rendering to our front end, we want all our data types to support HTML writable. So we would like to, we have to, not we would like to, we have to support HTML writable for all our data types, but our data types might also have other functionalities which might conflict with this sort of thing. So this is only available only for data types that we support, and we can only provide one implementation. So if we ever want to change the implementation of HTML writable, we would have to change the implementation everywhere on all the data types, which is a terrible thing to do. So this is tedious. This leads to bugs if we ever change our code base and so on and so forth. That was version 1, the object-oriented way. There are a bunch of other versions. Let's say version 2 with pattern matching. So we would have an object, which is essentially a singleton in Java terms. I'm going to call this HTML serializer. Let's call this pattern matching. And I would have to define a method. Let's call this serialize to HTML, and this will take a value. But because our values can be of arbitrary data types, because our data types might not necessarily be related, we have to support the any type, which basically destroys our type safety, because the any type can support anything. It can support integers, strings, and even data types that we do not want to support. So this would return a string, and I would say value match. And in case we get a person with a name, age, and email, then I'm going to return this sort of S-interpolated string, not a person, but a user, with a name, age, and email, and so on and so forth. And in case we get something else, we would throw some exceptions. So new illegal argument exception, let's say unsupported data type, which pretty much makes it a nightmare, because we also need to handle illegal argument exceptions all around our code base. So the drawbacks to this are that we've essentially lost type safety. So lost type safety. We still have one implementation for everything, because all functionality is pretty much crammed in this object. And modifications are terrible. If we ever need to modify the implementation or to support a new data type, we will need to modify this entire code base. I would honestly be afraid to touch this code. So this was version 2 with pattern matching, which is again a Scala feature, but this doesn't really work that well in this case. So enter version 3, which is type classes. And type classes are nothing but pretty much a design pattern in order to organize your code and modify or split the functionality in such a way that you can extend the functionality easily. But I think I'm hearing myself. All right. So we would like to decouple our code from the definition, the implementation, optionally provide multiple implementations, and make it easy to change what we want to support and how we want to implement that functionality. Let me give you an example. So let's say that we would like to implement the type class pattern for this sort of functionality. We would like to define a simple HTML serialization library that turns values into strings, let's say. So I would define a trait. Let's call this HTML serializer that takes a type argument. Let's call this A. And this has a single value. Let's call this serialize. So serialize, value of type A, and this turns that into a string. So this is, as I discussed earlier, this is like generics in Java. Serializer with angular brackets A, and once you've defined the type A, you can use it in the body of HTML serializer. Now, this is part 1 of the type class pattern. Part 1 is just to define the type class. So the type class contains all the types. So this is how I want you to think about this. HTML serializer contains all the types for which we have the serialization capability. So turning values of those types into strings. Now, we would support certain types and not others through part 2, and that is type class instances. So I would define something along the lines of a val, let's call this user serializer, as a new HTML serializer of type user. And I would need to override the serialize method. So override serialize. That takes a user and returns a string. And I'm going to simply decompose that. So I'm going to say val user with name, age, email is equal to value. So this is the kind of pattern matching deconstruction that you see in Python. For instance, you can deconstruct a tuple just by defining 3 variables into one line. And then I'm going to return the appropriate string. So this is what we call an instance of the type class, because this is a piece of functionality that implements the serializer for a particular type, which is user, and then we can use it later in external APIs. Except I'm not going to keep it a val, but I'm going to make it a given. A given means it's automatically being passed by the compiler to whichever method requires an HTML serializer of that type. So I'm going to say HTML serializer of user. So I'm going to have to add the type here, because otherwise I'm going to get a compiler warning. And notice that this code turned into gray because the Scala syntax will allow some shorter code. So I'm going to say with this sort of implementation. So this is essentially the same thing. So instead of making it a val, I'm going to make it a given so that this value is being passed to whichever API requires an HTML serializer of user. And that is part 3, the external API. So I'm going to, in part 2, you can define new HTML serializers for whatever data types you want to support, for users, for blog posts, for likes, for whatever. You can pictures. So here is where you define type class instances. So all the types that you want to support each have their own implementation. So notice how easily it is to decouple the definition from the implementation. Now, the external API would look something along these lines. I'm going to define an object. I'm going to call this HTML serializer. And this is a singleton object that is called a companion of this trait. There are a bunch of properties with these things, but just I'm going to create this singleton object that I can use as a static instance, a static as static methods in Java. And I'm going to define a method called serialize that takes a value of type A. And I'm going to have a value of type A. So this is, again, this is the external API. I would like the serialize method to only allow those types for which there is a using clause. And I'm going to call this HTML serializer of A. And this returns a string. And the implementation of this method is not really that important. So I'm going to use serializer.serialize on that value, but I'm going to collapse that because it's not important. I want you to hide that away. And whenever I want to call this serialize method, this will only be possible from the compiler's point of view, only for those types for which there is a given value of this type in scope. For example, I can say HTML serializer.serialize on Bob. Bob being my my first user. And this compiles and runs because we have a given HTML serializer of user in scope. So in this case, I can run this code and we'll see the same HTML as we expect. So notice we have div Bob 45 years old and so on and so forth. So we have the server-side rendering available for Bob, but, and this is the most powerful aspect of type classes, I can say HTML serializer.serialize, and if I pass in a regular value like 42, this doesn't even compile. Not only does that not run or give this some sort of bug or error, but the compiler prevents you from compiling this sort of code because the code is guaranteed to be incorrect due to the fact that you don't even have a serializer for that particular type in scope. So unlike the previous implementations where we used to throw exceptions and catch them, and we have this sort of spaghetti kind of code, hard to debug, hard to understand, hard to touch, hard to modify. In this case, the compiler is our friend because the compiler doesn't even compile our code. Not only that, but we can extend this sort of type class functionality with an optional part 4, which is extension methods. So I can define, let's say, an object. I'm going to call this HTML syntax. And I call this syntax as a good practice in functional programming libraries with extension methods, because we are essentially adding new pieces to the Scala language in this case. So I'm going to say extension, and assuming we have a type A and a value of type A, I'm going to define a method called toHTML that requires a using clause, so a using serializer as an HTML serializer of type A, and this returns a string. And the implementation is, again, not important. I'm going to use serializer.serialize on that value. So again, I'm going to collapse that. So once we have an HTML serializer in scope, we can say, and this is pretty magical, I'm going to say print line bob.toHTML. But this is only available if I import HTML syntax dot everything. And notice that once I've imported HTML syntax star, I have access to the toHTML method, which is only available for the right types. So only available for the right types. That is, those for which we have a given this sort of stuff in scope. And again, if I try running this sort of thing with the wrong type, like Scala.toHTML, this doesn't compile. toHTML cannot be used as an extension method. So this does not compile. So notice how flexible our code became because we untangled the definition, the implementation, and the API into one triad, which is the type class pattern. So this was the demonstration that I have for type classes. I hadn't prepared this earlier for the presentation, but I hope this makes sense given the magic that Scala has under the hood.
Thank you very much, Daniel, for just going in and giving yet another cool like definition and showing the power the power of Scala. Really nice. Thank you very much again, Daniel.
My absolute pleasure.